Hello, physical science students. This is Mr. Williams here, and today we are going to be talking about the history of the atom. Now, I know history and science don't really go hand in hand, do they? We mostly in science talk about facts, we talk about theories, we talk about proofs and how the whole universe works. And history is, well, truthfully, it's a little boring. It's just old dead guys and what they did and how it was important, yada, yada, yada. Well, science is built on that history. Science is a practice where over and over through the years we get better and better, and we get a better understanding of the world and how it works. And so that's what we're going to talk about today, and look at how the model of the atom, the smallest fundamental piece of matter, has changed throughout history. So let's just dive right in. So let's talk about what is an atom first. Smallest particle of an element retains its identity in a chemical reaction. So it's our tiniest little piece of matter. Remember, we looked at the difference between atoms and compounds, or elements and compounds. Elements are all the same kind of atoms. Compounds are two atoms, two or more. It's a ratio of atoms between different elements. They are kind of our bottom level of matter. Early philosophers, so way before science, we're talking like in the BC era, didn't have technology to see atoms, but they did propose ideas about their existence. And they formed models of how the universe might actually behave. Now before we go forwards, let's talk about what a model is. We see two different pictures right here. We have both airplanes. We have a big boy over here on the right and this Air Canada jet. We have this little tiny model airplane. Now, a scientific model is kind of like this, where a model is just an idea or just a way for humans to understand how something bigger and more complex works. So we today are going to talk about six main different models of atoms, and how they're different and how we've evolved our idea of what an atom is over time. And each has its own use. And that's really like a model airplane, because while we may not understand everything, if we can build a model airplane, that doesn't entirely mean that we could build an actual airplane. But a lot of the same principles apply. We need wings, we need an engine, we need a pilot in there. A lot of the same things will transfer over. And by building this, we will have a better understanding of this. So let's talk way back in time with our first model of the atom, Democritus. Before we do that, here's our six other models. First we have Democritus, then Dalton, then a guy named Thomson came along, then Rutherford, then Bohr, then the quantum mechanical model. These are our six different models that we are going to talk about today. You will notice that we are going to first start with Democritus down to our current understanding of the quantum mechanical model. Democritus was this first idea of atoms being proposed, and we've seen then over thousands of years, science changes and evolves over time. We've taken in more and more data, having better and better understandings of the universe, and developed new models based on our old, and out with the old and in with the new. Science does not just stick to one idea and roll with it. We change and evolve based on what data says. That's what science is all about. All right, let's dive into the first model on Democritus. Democritus' model was based on the idea of really just rationale. Democritus lived way back in the day, so we're talking 460 to 370 BC. So that's before we started taking modern record keeping, so not at zero. We're now in 2020. We're talking way back in the day. This was way before science was able of looking deep down into what atoms were, what matter was actually built of. But he proposed the idea based on just a leaf. He thought about, this is my drawing of a leaf. Oh my gosh, it's so bad. That's my drawing of a leaf. But imagine if you take that leaf and tear it in two, and then you take that piece and you tear that in two, and then you take that piece and you tear that in two, and you keep tearing. Well, he theorized that eventually you're going to get to something that you can't tear, that you can't cut into two pieces. He called those tiny little building blocks of matter atoms, atomos, and atomos is Greek for a meaning unable to and tomos meaning cut. So it literally translates to uncuttable. And he had no evidence whatsoever to support this claim. It was just an idea about how matter, eventually we just can't cut anymore. It took thousands of years before this had any scientific validity. This came from John Dalton, and his model of the atom is really the exact same as Democritus. He proposed that this is very real, that Democritus's claim based on nothing has scientific evidence. He did experiments. He collected both quantitative and qualitative. Quantitative means with numbers, qualitative means with words, descriptors. He took different kinds of observations and concluded that some form of an atom must exist. Eventually, you cannot cut things anymore. What Democritus theorized thousands of years ago, he was seeing in his data. But his idea of the atom was really no different than Democritus. It's what we call the solid sphere atom, that there is just some circle, some sphere of what makes an atom, and you just can't break that anymore. Now, then a revolutionary invention came along, and it's called the cathode ray tube. The cathode ray tube is essentially, think of it as like a laser pointer, but instead of a laser with actual photons being shot out, or like pieces of light, we are shooting pieces of electricity. And so how we do this is we hook up this cathode ray, which is the device here, and we hook it up to some kind of battery. So we have a cathode side and an anode. The cathode is the negative side and the anode is the positive side. And what happens when we hook it up to the battery is we get this beam of light. But like I said, it's not just light that's in there. And I'll talk about how we know that in just a second. Sir William Crookes first invented the cathode ray tube. He passed an electric current through a vacuum, and we see this beam of light is produced. And we know that the beam traveled from the cathode to the anode. So this is the negative side, this is the positive side. So we concluded that the beam must be made of negatively charged particles, little pieces of negative matter going from the negative to the positive. Because as we already know, negative is attractive to positive. Negative, given the chance, a negative charge will go towards a positive charge. Now, from this cathode ray tube, we developed a model of the atom because J.J. Thomson came along, took this cathode ray tube, and just did a really simple idea, which was put a wheel inside of it. He was amazed to find that the cathode ray, so shooting out like this, made the wheel turn. Now, if you would take a laser pointer and shoot it at a wheel like this, there's no way that that wheel's going to start turning because lasers are light and they are not made of matter. But this cathode ray is not made of light and it is made of matter, so these negatively charged particles have mass. And that led him to discover electrons. That's what he called these negatively charged particles. And then that changed our idea of how an atom must look. So Thomson's model of an atom looks something like this, often called the plum pudding model, because we thought of all atoms like an atom being a sphere of positively charged surface, and then little pieces of electrons were on the sphere. He thought that a cathode ray removed these electrons from the sphere and then allowed them to move into something else. Put them in that field was maybe made them change. So the plum pudding model, think of it like a chocolate chip cookie where the whole cookie is like the positive charge and then the little chocolate chips are negative. If you put it in a field or hook it up to a battery, we can rip those negatives off and make them do something. And that's what was going on in the cathode ray tube. Okay, so that's Thomson's idea. We evolved further to our main a really big step in our understanding of atoms was from Ernest Rutherford. And he performed a very famous gold foil experiment where he took a sheet of gold, and that's what we see right here. This is a sheet of gold, like a really, really thin sheet, and he shot alpha particles at them. Now, alpha particles are really, really, really tiny pieces of matter, and he shot them at this very, very thin sheet of gold just to see what would happen. And then he was able to detect where did those particles go. Most of them passed right through the gold foil, but not all of them. And so many passed through, but some scattered off in different directions. So think about what this must mean. Why can we pass through some parts, but not through other parts? Well, that led him to conclude that most of the atom's mass is in the center. And all the rest of the atom, the circle that makes it up, is empty space. He then concluded that what's at the center we now call the nucleus, and this is the positive part. We have a positive nucleus and negative electrons that don't just sit on that nucleus, but actually orbit around. So we got nucleus. Oh, he also came up with the idea of protons and neutrons. So inside the nucleus, we have maybe a proton with positive charge, a neutron with zero charge, and then orbiting around may be an electron. Both have mass inside the nucleus, those protons and neutrons, since they deflected some of the alpha particles. Okay, so that was Rutherford's idea. Now moving on further, we are moving on to Niels Bohr, who came after Rutherford. A Danish physicist improved Rutherford's model by hypothesizing that electrons live in orbits around the nucleus. So it's not all just scattered. So let's take another look at Rutherford's model in this picture right here. So these are just showing like all electrons just kind of orbit around at different, just random chaotic states. Bohr came on, and his big idea was that there are levels to the orbit. If you are closer to the atom, he theorized, this is low energy. If you are farther away from the atom, you are going to revolve higher, and you are at a higher state of energy. And electrons are at different levels depending on their energy. And then that has a really big, this changed our understanding of modern chemistry like ridiculously. We now understand why some atoms interact with other atoms and produce violent chemical reactions from Bohr's understanding of the atom. And then this brings us to our very last model of the atom, which is the quantum mechanical model. And this is kind of how we understand the atom today. This is the current accepted model. An atom's nucleus is composed of protons and neutrons. So we see that in here. Nucleus has solid particles. Some of them are positive, some of them are neutral. That's where almost all of the mass of the atom is. And now instead of electrons being particles that orbit around, it's more like they just exist in a cloud, that they are in a lot of places at one time. There's a whole probability that they could be anywhere. And that's what gets really crazy about quantum mechanics is there's no longer pieces and parts. It's all just like a spread of things. And so electrons do exist outside, but not in predictable orbits. They have this electron cloud. So although the quantum mechanical model is more current, the Bohr model is used to represent the atom. Why is this? So we understand like this to be true, that this is how quantum mechanics behaves, but that does not make the Bohr model useless. And like I said, the Bohr model changed our understanding of chemistry. This is what allowed us to understand like why do atoms combine and form in different ways. So we still use this atom today. Looking at the Bohr model, so because we still use it, this is the main takeaway from the Bohr model, that different energy levels can only hold a certain number of electrons. The very closest, we can only hold 2 electrons. Then in the second shell from there, we can hold 8 electrons, and then in the third shell outwards, we can hold 18. Even larger atoms have even more shells. If we have huge atoms, that's going to be like really big on the periodic table. But for now, let's just walk away knowing that different energy shells hold different levels, can only hold a certain number of atoms, and that these different levels correspond to different energies. All right, let's review all of the atoms that we have talked about today. We have, first, the solid sphere model, first proposed by John Dalton, really first proposed by Democritus, right? He was a philosopher who first made up the idea of an atom, and we still get the word atom from that first theory. But it was not scientifically proven until John Dalton in 1803. And that's just the solid sphere model that we have no parts to it. Then J.J. Thomson came along with help from the cathode ray tube to discover the plum pudding model. That's where we have this positive part of the atom with little bits of electrons stuck to the outskirts of it. And then Ernest Rutherford came along with his gold foil experiment and shot particles at the atom, and some passed through and some didn't. That developed the nuclear model that you can see there in the middle. Then we have Niels Bohr, who discovered what we now sometimes call the planetary model, really just the Bohr model, where these atoms, these electrons exist at different levels. And then finally we have this quantum mechanic model that the electrons exist in a cloud. All right, that is all the time that I have for you guys today. I hope you enjoyed this video. Please hit me up with any questions, or your other teachers, Miss McClelland or Miss Fawcett. We are always happy to hear from you and answer questions.